Hello everybody, welcome to video 12. Let's go ahead and get started and I'll jump to the share screen. So you guys are sharing my screen right now and we're in chapter 27. This is the last topic that we'll do for FUN 513 and this starts dealing with repeated measures designs. Let me take you guys first to this first program of chapter 27 called this mixed interpretation and just give you a little lay of the land of that. And when we get right there, STA 513, get to where you guys are at. And we're right here at this chapter 27 mixed interpretation. And let me just make sure I get the path all set real quick for my updated laptop. And when I go right here, this should get me to the where we need to go. So I'm gonna go ahead and load this data up. So this data is 45 observations, 4 variables. And I just print the data out. So we have this scale IIP and this score. And so basically in this plot here, I'm showing you guys the relationship between IIP and score. And let me just go ahead and save this. Just going to start SAS and new. Just get right back at it. Again, I just want to go through. We've done this all semester. But again, when I want to put the nums on, just type nums on in that box. And there we go. So we're going to go ahead and load this data up again. And like I said to you before, we're looking at the relationship between IIP and score. And in this case, we'll go to this simple plot. So the Y variable is the score and the X variable is the IIP. And namely here, we're trying to say, what can we say about the relationship IIP and score? Now, one of you guys has the IIP total score, and some of you guys have the Octant scores for the project. The IIP stands for Inventory of Interpersonal Problems. So these are people dealing with some problems. And the score, I believe, is depression. So as you guys look at this relationship, what can you say about what's going on average? And, if you look on average, it appears that, okay, as an individual's, interpersonal problems get higher, their depression gets lower on average. That's the appearance. Looks like a negative correlation when we're looking at it. And it's just kind of, okay, well, does that make sense? Like I said before, stats all communication. Does that logically make sense that somebody who has more personal problems will have lower depression on average? That doesn't make sense. That doesn't make sense from just a thinking naturally about this. And what you guys see is if I ran a simple regression model, this giving us the fitted model, right? So you can see there's the coefficient, that minus 0.645 is a regression coefficient. You see the R squared up there is 0.219471, right? So if I end up taking the square root of that R squared, it'll give me 0.468, but we see the coefficient's negative. So it appears, if we think of this in terms of a simple linear regression, that we're seeing an R squared, we're seeing a correlation coefficient of negative 0.468, right? That's what we say, and the data looks for that to be, to make sense. But I'm going to show you with Gplot what's really going on with this data. What's really going on with this data that you don't see is that the data consists of 3 repeated measures per person. And with the 3 repeated measures per person, the individual lines you see here are the individual regression lines for the 15 individual patients, where we're looking within that patient the relationship of IIP and depression. Now, when we look at this data correctly, when we see and count for that we have repeated measures, and we're basically looking at what's going on within a person on average, we see, okay, now this makes more sense. That on average, more interpersonal problems correspond to higher levels of depression. When we looked at the data previously, not accounting for this, it looks like not accounting for the repeated measures of the data, looks like a negative relationship. When we look in terms of the repeated measures, it looks like there's a positive correlation. So when not looking at the data correctly, you can get a wrong sense of what's going on. So what we're going to do here is we're going to fit the repeated measures data. And now what I'm doing here is, now remember, I have repeated measures within the person. So when we want to count for repeated measures within a person, we're going to use proc mixed. We use proc mixed already for random effects models, right? And with the random effects models, we use the random line to address when something was a random effect. We used proc mixed before with the repeated line when we were fitting heterogeneous ANOVA models. And in the heterogeneous ANOVA models, the big component here was the group on the right of the slash, where we had the group like treatment condition, which allowed different variances for each level of the treatment. What we're going to do here is really what the repeated measures was made, the repeated line was really made to do. And the repeated line here was made to accommodate the repeated measures per person. The repeated measures per person. Now, the R and the R core here are going to lay out exactly what, exactly the R will show us the correlation matrix of the repeated measures within a person. And the R will give us the variance covariance matrix for the repeated measures within a person. So let me stop share real quick and let me get to the information here for the Zoom session that we're looking on right now. Didn't know if I would need this, but I'll pull it up anyway. And we got the iPad going on at the same time as what we got here. So this is pretty cool. So we're joined in real quick here. So I'm joining without video. And I'm on the meeting. So let me get back to the share screen. So when you go to the share screen, now you can see here on line 83, I'm saying in this case, okay, I'm going to fit a variance covariance matrix which has the autoregressive design. Line 92, a Toeplitz design. Line 98, the unstructured design, and line 101, the compound symmetry design. Right? So they're kind of the big usual variance covariance matrices we use for repeated measures data. Now, those of you guys that took the time series class during the summer, in this case here, with the time series class, you were focusing on long strings of repeated measures that create a time series. For us, I'm going to go ahead and hit the stop share real quick and jump to the iPad just to write a couple things down. Is now the difference for what we're doing. What we're doing here is called repeated measures analysis, and it's also called a longitudinal data analysis, sometimes called LDA when we start doing it, or repeated measures as we start moving forward. So now for us, the big thing with the repeated measures data is we realize that we have repeated observations within a person. So just like we saw with the random effects model, we have 3 repeated measures within an individual in this example. So this 3 repeated measures creates a variance covariance matrix within a person. So it creates this variance covariance matrix within a person. So when we're modeling repeated measures data, the one thing we do is we make assumptions about the form of that repeated measures variance covariance matrix design. And so we have to model it. And when we're modeling it, we usually lean on a couple set structures. The set structures you saw, if I start from the bottom, was the compound symmetry, was the unstructured, was the toplets, and the first one we laid out was the autoregressive. We have to make some assumption about the design for the repeated measures data. Now, what the compound symmetry does, and if you guys have entered into the GEE version, the generalized estimating equation modeling for repeated measures of categorical data, there is a structure called the exchangeable structure, which is the common one used in GE analysis. The exchangeable is the compound symmetry. For us, the compound symmetry design for our 3 repeated measures in this example will assume a common variance for each observation, right? For each observation at the respective point in time. And it will assume an equal covariance between any pairs of repeated measures. So for us, the compound symmetry only requires 2 terms to be estimated. We got there, namely the variance and namely the covariance. So that's that one. When we get to the unstructured, this one's the most liberal of them all. And so with it being the most liberal of them all, it allows for unequal variance to be modeled for each point in time. It allows unequal covariance between any pairs of points. Now, with the variance covariance matrix, realize that this is, this is what we call a diagonal across the, well, I guess symmetric across the diagonal. So namely, the covariance between time 1 and time 2 is the same thing as the covariance between time 1 and time 2. The covariance between time 3 and time 1 is the same as the covariance between 1 and 3. And then similarly, the covariance between 3 and 2 is the same as 2 and 3. In this situation here, what you can see is we have 1, 2, 3, 4, 5, 6 terms being estimated here. We can go to the toplets next. And with the toplets assumes, in this case here, the toplets assumes a common covariance, a common variance at any point in time. And it assumes points equally spaced. Time 1 to time 2, time 2 to time 3, they're spaced by 1, have equal covariance, and time 1 and time 3 has its own covariance. So in this case here, the toplets is going to have 1, 2, 3 terms being estimated in the variance covariance matrix. And then we'll go here. We'll go to the autoregressive. So with the autoregressive has this design as well. And so the autoregressive assumes a common variance for every time point. Then between it's going to fit this parameter rho that you guys see here. But the rho, the covariance between A pairs of time points, the rho, the power rho is raised to is the distance between the pair of points. Now, rho is a correlation, right? So if you think about this, rho is a correlation that lives theoretically between -1 and 1, but we're assuming the repeat measures are positively correlated. So it lives between 0 and 1 if we think about this. But now, the further points are spaced from each other, so the further points are spaced, the less correlated we're assuming. Because you think about this, if rho's 0.8, that coefficient there is 0.8. Rho squared, 0.64, right? If this was bigger, rho cubed, so if we go rho cubed, 0.8, it's 0.512. If we go all the way to say 2 points are 12 points across, maybe like 12 months, then we go 0.8 to the 12, that would be 0.069. So in this setup, the autoregressive has this quality, which we see in a lot of data, that it assumes points closer together in time are more correlated than points further apart in time. So, I think that's really a really good, really good use of, of probably reality with the data. In this case here, This only has two parameters being estimated. The variance term, and then this correlation term. So that has two. They're the common ones. The further you get into repeated measures, remember this is just an introduction, you can see a lot more flexible variance covariance matrices. So in this case here, let me go ahead and clear these drawings. So now if we get here, the thing we have to remember is there's the compound symmetry, right, which in this case comes with two parameters. The unstructured with 6, the toplets with 3, and then the autoregressive with 2. Right, so there's the number of parameters. One of the key things we're going to see is which is best. The unstructured makes no assumptions about the variance covariance matrix, whereas the compound symmetry and autoregressive are making things a little bit more manageable, I guess. So which is best? We need some goodness, or I guess we could really think of this more, we need some sequential way to test this. Right, we need some sequential way to test this. One way to test this is going to depend on the form, the number of parameters estimated, and some fit statistic. We're going to see that ProcMix is going to kick out a bunch of them. One's going to be the -2 restricted log likelihood. One's going to be the AIC, the key information criteria. One's going to be the AICC, and the other one's going to be, I'm running out of real estate here, the other one's going to be the Bayesian information criteria. This one you guys see right here, the AICC, this is the key information criteria corrected for small sample sizes, which this one is, as you see. So now I'm going to just go ahead and stop the screen share, and then we'll get back to the iPad share, and we'll get back to where we were. So what I'm going to do is I'm going to fit each one of these sequentially. Now, the reason I got pad ID here is it's going to allow, if you think about it, in each graph that we had here, each person's intercept, where IP 0, each person's intercept's unique. So throwing the pad ID into the mix will allow me to estimate individual intercepts for each person. Now, usually pad ID is the unit. In this case here, the unit is the patient time point. So we'll go right here and fit this. This one's going to fit the autoregressive. And let me show you what the output does. Again, like we saw in chapter 25, we're using the Satterthwaite estimation approximation. So when I go ahead and fit this, here we go. So when I fit this, here's the coefficient for IIP. So on average, we see a positive coefficient. It says for every unit increase in IIP, inventory interpersonal problems, depression increases by 2.64 units on average. And again, we're fitting one common estimate across all patients. So we got that, but let me go through the whole output. So for these 15 patients, the R gives us this form of the variance covariance matrix, right? So namely, for each person at each time point, we assume a variance of 9.16. The covariance between points 1 unit apart is 1.1312, and the covariance between points 2 units apart is 0.1396. Below gives us the variance covariance matrix. My fault, the correlation matrix. So with the correlation matrix, you can see the correlation here is 0.1234 time 1 to time 2, 0.0152 time 1 to time 3. So that's what we got right there as we start moving forward. So that's cool. That's cool. We got this here. This is showing us the estimates of the variance covariance matrix, right? 9.16, 0.1234, right? And if you notice this 9.16 is the variance at any time point. The 0.1234 times 9.161 gives us this. This 0.1234 squared times 9.1641 gives us this. So the R gives us the variance covariance matrix, and the R core puts the variance covariance matrix into a correlation matrix. So like we saw with the random effects, we're assuming that the variance covariance matrix is this form for all 15 of the patients. If we drop a little further, here's the fit statistics. These fit statistics are worthless unless we're doing some kind of comparison. Now, all 4 of these can be used at some time or the other. All 3 of these are variations of that. You know, you guys will have to lean on your statistical analysis plan about which technique you're going to use for goodness of fit. What we do here applies to any of them. So right now, we're going to use the -2 restricted log likelihood. So in this one, for the autoregressive, which use 2 parameters, this gives us a -2 restricted log likelihood of 164.8. So we got that there. No, highly significant association. The Sareth weight, this is giving you degrees of freedom that can be decimals. So that's fine. I'm going to go ahead and highlight this and unhighlight the toplets. So when I fit the toplets, so with the toplets, you can see here are the 3 parameters we assumed would be estimated. And so namely, between points, you know, in this case here, you know, if we start going here, in this case, so here's my variance at each time point. This represents the covariance between any pairs of data 1 time point apart, right? So in this case here, there's the covariance 1 time point apart, and then here's the correlation for 2 time points apart. So we got that all figured out right there. And then the toplets gives us, you can see 164.8 for the -2 restricted log likelihood. I'm going to see if I can get the, here it is. So put in terms of decimals, the toplets is 164.763. If I go to the one above, this one's the compound symmetry. This gives us my fault, this gives us the autoregressive 164.76 2698. The toplets, if we go here, so the toplets is 164.76269799. So we have to really go pretty far out for the decimals to show any sizable improvement in fit. Let's go ahead and go to the unstructured and show you guys what that does. So with the unstructured, we fit this. And so with the unstructured, we're right here, right? So if you go here, the UN11 is the variance of time 1. UN22, the variance of time 2. UN33, the variance of time 3. UN21, the covariance between time 1 and time 2. UN31, the covariance between time 1 and time 3. And UN32, the covariance between between time 3 and time 2. This is showing us the standard variance covariance matrix for patient 1 and the respective correlation matrix. So like you said, I guess one of the weird things is between time 2 and time 3, they're negatively correlated, which is kind of curious, but that's cool. That's cool. Still get the results here. Let's see what the fit is if I go all the way up to here. So for this one, for the unstructured, it's 162.7000398. So we got that there. And then let's do the last one, which the last one is going to fit compound symmetry. So when we fit compound symmetry, this one won't estimate, and it won't estimate. So we lost the fit on that. So stop because of infinite likelihood. So that's cool. So we're able to fit all those models. So again, keep an eye on the notes. The R prints out the variance covariance matrix of the repeated measures. The R core prints out the correlation matrix. The sub or subject flags the variable in the data where we have the repeated measures. So autoregressive assumes an equal variance each time point, but assumes points closer in time or more correlated points further in time. The Toeplitz design assumes equal variance each time point, assumes equal covariance correlation between any pair of points equally spaced apart in time, but makes no restrictions about whether points closer in time or further in time have bigger covariances. The unstructured, like we said, the unstructured on line 98 is the most liberal of them all, allows all separate variances at each time point and separate covariance correlations between any pairs of time points. Then the compound symmetry matches the exchangeable design of GE, if you guys have hit that yet, assumes equal variance each time point and equal covariance correlation between any pairs of time points. So we just fit all of those models. So for us, before we even, so we fit all those models, for us, still the question becomes, which is the better fitting model? And the one way we do that is we get right here. On D2L, you will see this, what I call, if we get here, what I call, I'm trying to trying to move this. Maybe it's better to go here and show you. This is called chi-square fit of nested models. What we're basically doing is we're making more restrictions to some of the variance covariance matrices. So for us, what we need is model A minus 2 restricted log-limited AIC, AICC, BIC. Whichever one you want to use, just stick with that consistently. So for us, I'm going to go ahead and look at the unstructured, right? So in this case here, the unstructured design, right, which gave a minus 2 restricted log-limited of 164, my fault, 162.7000398. The unstructured required for us in this case here, it required 6 parameters in the variance covariance matrix, the variance at each of the 3 time points, covariance 1 to 2, covariance 1 to 3, covariance 2 to 3. So there's the 6. I'm going to compare this to, in this case here, to the autoregressive design, right? The autoregressive design. And again, if we're keeping an eye on these, let me just run it really quick. I'm going to run the unstructured really quick. So when I get here and run the unstructured, right, we get right here, we got the minus 2 restricted log-limited, which we got it to more decimals even here. But the big thing for us is you need something to compare it to. And so in this case here, the model I'm going to compare it to, and before I even jump in this, right, that's the minus 2 restricted log-limited. So remember in 506, I guess maybe in 505, I can't remember when you got introduced to likelihood, but the likelihood function represents the joint probability the observed data comes from the assumed model. That's the likelihood. Then you use log likelihood and maximum likelihood estimation, which made it easier a lot of times to find the MLA. But the big thing is, in this case, we want the likelihood to be as big as possible. The log function, right, that's monotonic. So when the log's as big as possible, or the log likelihood's as big as possible, we're finding the maximum likelihood estimators, which we were trying to do. For us, kind of mimics that situation where we got the minus 2 restricted log likelihood. So the likelihood function, again, in this situation, is the joint probability the observed data fits the assumed model. Right? So again, it fits the assumed model. So in this case, the bigger the value of the likelihood function, the better the fit. The bigger the value of the log likelihood function, the better the fit. When you multiply that log likelihood function by minus 2, this now means the smaller the value, the better the fit. Well, we could see here that the unstructured comes with a minus 2 restricted likelihood of 162.700. When I go here, I'm going to compare that to the Toeplitz model. And with the Toeplitz model, if you remember in this case, this Toeplitz model gave us a minus 2 restricted log likelihood of 164.7626. And the Toeplitz model came with 3 parameters estimated. So this is the difference in the parameters and the respective p-value. So this is saying to us, if the model with the less number of p-values has a lower -2 restricted log likelihood, it is better fitting. No need to check the p-values in this case. When there's more complexity, more parameters, having a lower -2 restricted log likelihood, we're looking to see if there is a significant gain in fit. If the p-value is below the alpha level, then there is a significant improvement in fit, and we'll use the more complex model, which is the one with the more number of parameters. If the p-value is greater than or equal to the alpha, then we don't have sufficient evidence in our data to warrant the more complex covariance structure. Therefore, we will assume the toplet is as good as fitting, is not a significant loss in fit compared to the unstructured. Well, from here, we could compare now the toplets, which require 3 parameters. I'm going to compare this to the autoregressive. If you guys remember, that -2 restricted likelihood was 164.762698. Right, the autoregressive came with 2 parameters, which gives us that difference with that p-value. So again, each row, we're comparing a variance covariance matrix with more parameters compared to a variance covariance matrix with smaller number of parameters. And we're trying to see, is there a significant gain of fit by the more complex model? Whether or not this p-value is below the alpha level will tell you that. And if it's not, then we will assume the more simplistic model is sufficient for modeling the repeated measures data. But we just got that right there. So we just saw that right there, that we ended up getting that comparison. So for us, in this case, if I just take these guys out, for us, in this case, what we ended up seeing is the autoregressive was appropriate. We did not need a more complex variance covariance matrix to fit the repeated measures data. So that's cool. That gets us to where we need to go as far as fitting. So namely, the most appropriate model for fitting these repeated measures was the autoregressive design. And when we fit this, we can see real quick here, we get the model working fine. This gives us the relationship between IIP and depression, which is highly significant. You're seeing the Satterthwaite parameterization of the degrees of freedom coming in where you can get decimals. So that's cool. That's cool. Again, if we ignored the clustering of the data, we got a negative relationship, but when we account for the repeated measures, we have a positive relationship. So again, like we said, for fitting the best variance covariance matrix, we fit each model separately, changing the variance covariance matrix design. When we're looking at the output, the only thing we're looking at is the respective fit statistics and the number of terms in the variance covariance matrix estimated by each. So again, to compare between 2 covariances, we look at the difference of the -2 restricted log likelihood or the AIC, the AICC, the BIC, whatever's written in your guys' data analysis management plan. We'll use the -2 restricted log likelihood as we deal with here. But again, you'll look at that difference in the -2 restricted log likelihood follows a chi-square distribution with degrees of freedom equal to the difference of the number of parameters. So if that chi-square is significant, then the more complex structure is warranted and therefore fit.
If the chi-square is non-significant, then we don't have sufficient evidence indicating the need for a more complex structure. Therefore, we will assume the more simplistic structure is sufficient for modeling purpose. And again, we could use this Excel template, which you guys see on D2L, to be able to figure out what the best variance covariance structure is for the data in hand. So it's pretty cool. I know it took us about 45 minutes on its own, but that's fine. Now, for us, when we start talking about repeated measures, you know, in this case here, classic university statistics assumes each data point gives rise to a single measurement. So everything we were doing before chapter 25 were single measurement assessments. They were the outcomes. They were the whys. They were the whys. Now, if you guys take the MANOVA class, the multivariate analysis variance, what this goes about is not fitting repeated measures in a sense, but in this case, simultaneously modeling at a specific time point multiple measures as y. Or in other words, these measures are a vector of y, where the first dimension in y is the Beck Anxiety Index, the second's the Hamilton Rating Scale, the third's the Inventory Interpersonal Problem, and the fourth is the Beck Depression Index. We're not going that route. What we're going is we're looking at the situation with the third bullet. So each subject gives rise to multiple measurements of the same outcome of interest, measured in some kind of timing point. So each measure, example, measure each subject on the Beck depression at 5 consecutive sessions after administration of the first treatment. That's the typical longitudinal data that you guys will see a lot of times. The big thing, let me go ahead and I'm just going to stop share for a minute and get back to the iPad. The big thing, the difference between, I'm going to call it longitudinal data analysis, LDA. So the big difference between LDA and time series all goes to the shape of the data. The time series, I think of this data as longer than wide. And what I mean by that is, if we talk about repeated observations on person, there's more people than time points. So in other words, there's more rows than columns, where columns are identified as different timing points. The time series, is more this way. The time series is what we call wider than long, right? So this is the various time measurements. And then the rows correspond to whatever outcome you're modeling, whether or not it's a stock price, whether or not it's daily observations, daily measures. But the big thing in this case, time series, in this case, the columns are much bigger than the rows. For LDA, it's the flip. We have more rows than columns. In time series, you have more columns than rows. So that's the big difference between LDA and time series. So again, we see that there. So longitudinal studies. The big thing about longitudinal studies is they have the ability to get a sense of time,
where this time could be some kind of cohort progression through stages or some kind of aging effect. The cross-sectional data is just one cut, just one cut. So, like with the cocaine study, month 3, we're cutting the data at month 3. Month 6, we're cutting the data at month 6. But the big, big thing of longitudinal studies, it can allow us to look at the effect over time. Sometimes this could be called an aging effect, right? Again, cross-sectional data won't be able to give you that change over time feel. The big thing with the longitudinal data is, again, it's going to require us to use statistical methods, because now like we saw with the random effects model in chapter 25, the data now is no longer IID. It's no longer independent and identically distributed. We have the repeated measures within a person. Those repeated measures are correlated. You're dealing with the same person. So when the within subject correlation is properly modeled, right, it's going to give us the most appropriate results. And in fact, when we use the repeated measures data, we actually get more statistical power. And those of you guys who progress to the LDA class, I'll show that discussion to you when we get there. But the most important thing is the last bullet. Our job is to model the data, not throw the data in the model. If you model the data, if you throw the data into a model that does not take into account the clustering, then every p-value you derived is flawed. They're worthless. Because again, our job is to model the data, not throw the data into a model. So the big thing is the covariance structure. Like anything, we're trying to get to some sense of parsimony, right? But the variance covariance matrix wants to be able to get that residual variance as one component, so the variability not explained by the model. And we also want to take into account the whole clustering of the repeated measures. Now, in the repeated measures design, you could look at this in 2 ways. So for the repeated measures design, you could look at this in 2 ways. And the 2 ways are as follows. You could look at it in terms of, okay, with the repeated measures, we could look at it in terms of an LDA analysis, which in SAS would use the repeated line. Or you could think of this as, in this case here, with the LDA using the repeated line, or you could actually even think of this as a random effects model. And namely, with the random effects, we know the patients are chosen at random. So in this case here, the unit of the data is the time point for each person. And then these time points live within a person, and this person there's a person that lives above that as far as getting the data. Right now, we're going to just really focus right now on this leveling. This basically two-level nesting rather. In this case, the levels, level 1, the within person level, and then here we start getting after the between person level, right? So that's 2 ways of thinking about it. Now with the random effects model, the one reason we don't go that route entirely is it restricts the variance covariance matrix and forces it to be forces it to be compound symmetry. The LDA, we have a little bit more flexibility with the variance covariance matrix. But again, you know, you think about it in terms of this way or that way. I think, you know, modeling the variance covariance matrix manually with that repeated line is going to really uncover a lot of the important stuff for us. So you can look at it as a random effects model with a time point within a person as level 1, which again, the source of variability, the error variance is linked to that level, and then level 2, the person level. When we're modeling some of these, well, initial approach tried to use the sums of squares. For us, we're really going to focus more on the variance components, the variance between and the variance within subject. Now, with chapter 27, they talk about checking the appropriateness of the repeated measures design. Again, I told you guys before, you know, there are some topics the book uses or some statement the book uses that doesn't make sense to me on a day-to-day life as a statistician. This is one of these. You know, here, if we have repeated measures, we have to model it, right? If it's part of our data, we need to model it because it handles, you know, the hierarchy of, it really gets at, you know, really modeling the data. So again, I don't understand how you're going to say, is it an appropriate design? It either is or isn't. And for the data I give you, it should be pretty clear. The data you get out there working, it should be pretty clear. If not, you ask questions, right? Nobody's going to hurt you for asking a question. The big thing with longitudinal data, it's really important. It's that extra information, and especially if it's time, we get to talk about some sort of timing effect, agent effect, or even a cohort effect. In this setup, it's proc mixed, and just like GLM, you bring in covariates, you know, predictors, interactions. So everything we did before in proc GLM, we do in proc mixed. You know, the only thing is proc mixed, as we saw before, has an Ellis mean statement, but not a mean statement. Well, in analyzing repeated measures data, you know, a lot of people try different approaches. The endpoint LOCF, fixed effects ANOVA, basically ignoring the clustering of the data, repeated measures ANOVA, generalized estimating equations. We're going to look at one of the topics. So the very next topic is going to look at the mixed effects ANOVA model. And we're going to look at that as closing out the course. Hierarchical linear models, which again is a part of the LDA course. With the endpoint, or a lot of times called endpoint or LOCF, which stands for last observation carried forward. In analyzing repeated measures data for the longest time, people would go this route, the endpoint LOCF. And the big thing with that is, you know, if you add the repeated measures data, we're throwing away so much data. And we're considering the last outcome for an individual and considering that as our outcome of the analysis. Well, what if there's a differential timing of that last time point? So in this case here, the endpoint LOCF seems a little flawed. Additionally, it assumes no treatment effect once the dropout or the missingness has begun. And you know, so it doesn't accommodate the effect of differential attrition. So it assumes missing data is not informative, and what to do. The big question though is, okay, if it's not informative, but what do you do if there's no post-baseline data? You know, from an us perspective, that's not, you know, for us, it doesn't really matter. You know, we just lay out some of the restrictions, some of the worries of the model. The fixed effect ANOVA does not take into account the clustering of the data, just assumes that variable time as a fixed effect predictor in the model. That's not right. The repeated measures ANOVA in the multivariate class, you'll talk about this. This is a repeated measures approach. But with the repeated measures approach, it models the vector of the outcomes, but it assumes the variance covariance matrix between any repeated measures within a pair follows that compound symmetry design. Additionally, it requires that we have complete data. Complete data. So the big thing for the reason for a repeated measures design is, the big thing is effect over time. How does an intervention accommodate change over time? And that's what we want to do. The big thing with the repeated measures design is, okay, there's no real sums of squares approach. So we got to really lean on the repeated measures about how the repeat measure software about how the variance is being divided up. The big thing is when we have repeated measures, it's new information. Now, does that it's new equal a new person? Not really. So for us, repeated observations are almost like data. How much is it like new data all depends on that within subject correlation. That within subject correlation 0, well then that's pretty good. That's a pretty good, like it's a new body. If the correlation's 1, then we're gaining no information. The big thing with the repeat measures, we need to know where the repeated measures are coming from. Where the repeated measures are coming from are called the subject variable. When a dependent variable is measured repeatedly for all sample members across the set of conditions, this is what we call a within subject factor. So again, things like time are what we call within subject. When a dependent variable is measured on independent groups of the same member, then each group is exposed to a different condition. This set of conditions is called the between subject factor. And when the analysis is both within and between factors, it's called a repeated measures model. So let me show you guys this next one. This is from the cocaine. Now, this one's not the cocaine addiction trial. So this one has 8 subjects. We have 1 between subject independent variable called group. We have 1 within subject dependent variable, really the time that we're looking at DV1 to DV4, and 1 dependent measure. So in this case here, I'm going to go ahead and open up this program. So we go here, this mixed model ANOVA intro, right? So in this case here, I'm going to go ahead and load this data up. This data right now is a flat file. And what I mean by flat, each person is 1 row of data. The repeated time points are the last 4 columns. So now for us to use proc mixed as the repeated measures modeling platform, or whatever you guys, if you guys are using, the LME4 in R, XT mixed in STA, we need to turn this data into what we call a stacked file. And right here, you use proc transpose, but namely, I'm creating a variable dv for dependent variable, and I got a variable trial, which indicates the time point. So if you look at these two back to back, here is our original data, but the stacked file takes this DV1, DV2, DV3, DV4, and puts it down the column in that table. So let's just eyeball what's going on with the data. So this is showing us each of the 8 subjects over time, regardless of the group. That's sometimes just called, simple plots. Here, if I put them on top of each other, right? So in this case here, dependent variable for the 8 bodies. And then if we go here, it's giving us a smooth trajectory. So it kind of looks like we kind of have like almost like a trigonometric sign. We go up at trial 2, come down to trial 3, and start working our way back up. And here, all right, so in this case here, we have 4 and 4 observations for each of the 2 groups. And then if we look at this, these 2 plots are giving us separate plots for intervention 1, which is supportive expressive, intervention 2, which is cognitive therapy. So we're right here. All right, so in this case here, let me just put, so this is showing us 2 smooth graphs. So it seems like, I don't know if we're going to have a group by time interaction. I think we're going to have a time effect, but I don't think a group or group by time interaction layout. Now, for those of you who will see repeated measures ANOVA performed, in ProcGLM, to fit a repeated measures ANOVA, on line 173, we're putting the repeated measures. If you're using repeated measures ANOVA within GLM, this is going to require the data to be flat. So you can see I'm on the flat file here. So when I model this, it's going to give me a lot of output. So I'm going to go up to the very top. Right, so we're coming down on the top, showing us a little layout of the variance covariance matrix. In this case here, this is giving us the effect of time. So most people lean on the Wilks lambda as the test statistic under this platform. So we see a significant time effect. Doesn't come as a shock. This is looking at the trial by group effect. Again, a little bit of a trend. And then in this case here, this is looking at the between effect for group, which is non-significant. So namely, the big thing we say is that there's a timing effect, and actually this is giving us a timing by group interaction. Timing by group interaction. So again, you could do that. You could take the repeated measures ANOVA and ProcGLM and make this a MANOVA. Now the MANOVA with line 182, right? The repeated measures ANOVA, line 174. The multivariate analysis variance in ProcGLM is being specified on line 182. So while this assumes a compound symmetry design, the MANOVA makes no assumptions about the design. And so again, if we go to the top, so at the top, SAS will pull out, basically one-way ANOVAs for each point in time. But once you get here, this is where we're starting to model the variance covariance matrix. And in this case here, this is looking at, the new, more complicated variance estimate. So this one's looking at the timing effect, highly significant. The time by group, a trend, and then the group effect, non-significant, and the, hold on for a minute. Okay, then we're back at it. Just had to take care of something real quick. So in this case here, we get the trial effect, and then anything that's going on. The group effects right here, which is now non-significant. The one thing with the MANOVA, the repeated measures ANOVA assumes a compound symmetry design. The MANOVA assumes an unstructured design. But these two approaches require complete data. You need complete data. For us, again, I'm just going to look at this really quick again. Right, so this is the repeated measures ANOVA. So with the repeated measures ANOVA, we can see here that the affected trial group is 0.0067. Trial is less than 0.0001. And then we slide up a little bit more, and the group effect is 0.5506. So we see that filled out for the repeated measures ANOVA. This guy here is doing the repeated measures model. Line 199, we're telling SAS it's repeated where each new trial indicates a repeated measurement. So where the trial really measure the time. And I'm telling subject equals sub, so unit identifier sub, and we're fitting the compound symmetry design. When I do this, we end up getting to, in this case here, right? So here comes the variance covariance matrix and all that. But here's the group effect, 0.5506. Exactly what we saw on the ProcGLM repeated measures ANOVA. The treatment off the charts, less than 0.0001. We see that here. And then the group by trial, 0.067. We see here. So the repeated measures ANOVA, I mean, the model we did previously and within SAS, this repeated measures model actually counts for modeling the variance covariance matrix. And we told SAS we wanted the compound symmetry. So that's the compound symmetry design, as you guys see here. One thing to keep in mind, if we fit this with a random line, if we did that with a random line, so what you guys would see in this case with the random line, we would see in this case here, the group by trials, 0.067. The treatment is off the charts. The one that changes a hair here is the group effect, which before had a 0.5506, now has a 0.5353, which is linked to how the degrees of freedom are being estimated. So if you guys see here, I walk through how to get the best covariance matrix here with a little help from SAS. I'm turning the listing off. I'm leaning on line 235. Sometimes this is how I fit repeated measures data. I don't look at any of the output. I turn the output off, and I start building on getting these information criteria data set for each possible variance covariance matrix. So this one is doing compound symmetry heterogeneous, autoregressive, toplets, unstructured. So I just ran those, right? So here I'm creating another where I put all the information together. I could print this out now. Now with this printed out, I got the -2 restricted log likelihood right here. I have the number of parameters and any of the other variations you want. Then I could use this to decide which is best. So in this case here, I'm going to go with in this case, the most complex unstructured, which is 115. With the unstructured, we saw that required 10 parameters. And then I'll go to the next one. So with the next one, the next more complex is compound symmetry, 129.7. So 120 is it? It is 119.7, right? So in this case here, if I go back to SAS, this required, in this case here, the compound symmetry required 5 parameters. It says 5 parameters. We're looking at compound symmetry heterogeneous. So when I go here, I put 5, right? So we see there is not a significant difference in gain of fit by going from unstructured to compound symmetry heterogeneous. I'll use this next. I'm going to compare this to the next most complex variance covariance matrix. So in this case, I'll do I'll do I'll do the toplets, which is 120.2 with 4 degrees of freedom, right? So I'm at 120.2 with 2 degrees of freedom. So there, we get there. So again, we go back to the output. So unstructured, we compared that to the compound symmetry. We now compared it to toplets. And now, suppose these were your only 2 variance covariance matrices to choose from. Anytime the number of parameters are the same, the model we want is the one that gives the smallest -2 log likelihood, or AIC, AICC, BIC. But again, to do that, in this case here, the smaller, the better the fit. So the compound symmetry is the better, 2 degree of freedom approach, right? So in this case here, so if we get here, we go, okay, 119.7, that's 5. And then we compared that to, my fault, 120.2. 2, and then who do we want to compare it to? Let me just get it printed out again. So the 120.2, we'll compare this to the 121 with 2 parameters. So now compound symmetry is better fitting than autoregressive. Same number of parameters, it's the one with the smallest value. So let's go 121. 121. 121 point 121, I guess, 0.0. Yeah, it's 121.0. In this case here, right? And in this case here, right, so in this case here, we end up getting the smaller one, ends up fitting best, which ends up being compound symmetry in this example. So that's cool. Again, we just looked at this. Does the trial impact the outcome, namely the time effect? Do the treatment groups impact the outcome? Is there an impact of trial on outcome? So this is the interaction component. Again, the proc GLM we just looked at. The big thing with this syntax is it requires the data to be flat. Again, it assumes this compound symmetry, which assumes equal variance between any pairs of time points. And for us, the repeat measures nova can be set up to account for other issues like categorical data. When we fit the repeated measures through GLM, we really should be looking at the overall Wilks lambda. Again, look at univariate results. Why? When we break down when we do the cross-sectional cuts, we're kind of throwing away the longitudinality of the data, which we don't want to. We want the longitudinal period portion to still be involved. Again, the MANOVA layout has a variance-covariance matrix of unstructured. The big thing is cases with missing value at any trial are dropped off, so ProcGeom will automatically delete the entire observation, no matter how many values are missing. Again, we're counting for the variance covariance matrix of the repeated measures. So basically what we're doing is we're bulking up beyond a paired t-test. This is a key syntax. For us in this chapter, the repeated line is crucial. So the repeated line, some of the output, like I said, R prints the variance covariance matrix. R cores the correlation matrix. Subject ID type equal compound symmetry, kind of typical. Our focus is on what we call the R matrix, not the G matrix, but the R matrix, and truly modeling that. When the outcome's only one time point, the R matrix reduces down to the MSE. So some shapes and forms of the R. Independence assumes no correlation. Don't know why we do that. This compound symmetry, like we said, equal variance each time point, equal covariance between pairs. The autoregressive, we get the common variance each time point. The covariance, and then we got, the correlation term being raised by the elapsed time. So we said Toeplitz pooled variance, but separate covariance between pairs of points spaced differently over time. Unstructured makes no assumptions. And the big thing is we're extending the general linear model to what we call the general linear mixed model. And the big thing for us is really modeling that variance covariance matrix. So we're on this path from where we began back in topic 0. So again, the big thing is the class statement, the model. We've worked with ProcMix now. Everything's the same except we got this repeated line that we need to keep in mind as we move forward. So again, the ProcMix, again, just business as usual. Like I said, I think a couple of these might be repeating. The R, print the variance covariance matrix. The R core, correlation matrix, subject the patient identifier. So our focus is usual on the R matrix. When the outcome's only one time point, the R matrix reduces to mean squared error. The big thing is we can be flexible on the forms of the R. But when we're modeling, it's just like a pooled error, pooled MSE to model the data. Again, there's the independence, compound symmetry, autoregressive, templates, unstructured. These last four are kind of the typical layout of repeated measures. We're going to take one more look, and that's the next topic that we'll do shortly. So thank you very much, and I'll see you at one last video to close the course. Thank you for your attention.